The next speaker, so Marta Sanz-Solé from the University of Barcelona, and she's going to talk about hitting probabilities for systems of stochastic claims.
As you know, on the 3rd of June, Paul Maliaven passed away, and to many of us it has been an incredible source of knowledge and of problems. And at a more personal level, I have always admired his incredible amount of energy, also his wisdom, and also his scientific vision. So my lecture is dedicated to him. We will deal with, in this talk, with stochastic processes which are indexed by a parameter which is m-dimensional and take values on a RD space, a d-dimensional space. And we are interested in the following question. So you define the range of V on a compact set I as being the random set given by this set. And then the question is what can be said about the hitting probability of the process the set A, so the hitting probability to A, in terms of properties of A, which came from geometric measure theory, like, for instance, the capacity or the Hausdorff measure. So this is a very common question in probability theory. You encounter hitting probabilities, for example, when you study elementary properties of Markov processes, like recurrence or transience. But this is in the core of the probabilistic potential theory. So this is a question in probabilistic potential theory. And so when I say what can be said about, I mean to find precise upper and lower bounds described in terms of the capacity of this set or the Hausdorff measure. So if one has information about this problem, then one can easily get a characterization of the polar set, and this is very important in potential theory because, for example, this can help to characterize maximal positive solutions to elliptic equations. And also you can have consequences about results about the Hausdorff dimension of the range of V, and also answer questions on the level set. So this is a crucial problem and also a difficult problem. So I guess that many of you are not maybe very used to use a capacity and Hausdorff measure, so I will give just the definitions we are going to use here. I will only deal with a specific case of capacity, which is the vessel risk capacity. And for this, you need to know what a vessel risk kernel is. So this is the definition of a vessel risk kernel. And then you define the energy in the following way. The energy is a notion which is associated with a probability, mu. So you consider a probability who has a support on E, and the energy, by definition, is this double integral here, okay? And then the capacity of the set E is defined as the inverse of the infimum of the energies when mu belongs or runs on the set of probability measures on E. So this is the capacity. So you can very easily verify that if the set consists of a single point, so if it is a singlet on E, then the capacity is 0. That means small sets have a small capacity, so to say. And for example, if a set has a positive capacity, means that there exists a measure, mu carried by E, with finite energy. So this is the interpretation of a positive capacity. So as for the Hausdorff measure, it depends also on the parameter beta. So if beta is positive, so this is the interesting case, the Hausdorff measure of the set is defined as follows. So you take a covering of the set A given by balls centered at xy with radius ri, and the radius is small. Okay, and then you sum up the diameters to the power v and take the infimum over all coverings, and after that the limit as the radius tends to 0, and this gives you the Hausdorff measure. In the case where beta is negative, then you just give the value infinity. So Hausdorff measure is related to Lebesgue measure. For example, if beta is an integer, then you get Lebesgue measure. If beta is equal to 0, then you get the counting measure. So apparently, both results, or both definitions, sorry, are not connected. But this is not true. So they are really connected, and well, one connection, for example, is given by one of Frossman's theorem, which state that if the capacity of a certain degree beta 1 is greater than 0, then so is the Hausdorff measure, and the converse is almost true, except that you have to take another slightly smaller parameter beta 2. Okay, so this fact will be used in the proofs of or results, what gives to give a meaning to all results. Okay, so let's try to give an answer to this problem for stochastic processes which are popular. And I think that maybe one of the most popular examples of stochastic process is Brownian motion. So for Brownian motion, if you consider a d-dimensional Brownian motion, then there is a null result by Kakutani and then by Dvoretsky, who says that a Brownian motion hits a set A with probability, with positive probability, if and only if the d minus 2 capacity of the set is greater than 0. So here, the two, you may understand these two as being the order as alpha stable process. So Brownian motion is an alpha stable process with alpha equal to 2. Okay? So in particular, you can characterize, so you can say when a singleton is a polar for the Brownian motion. You have this result, which is a consequence of the fact that I have mentioned before about the capacity of a singleton. Okay? The proof of the results uses very much the structure of Markov process of Brownian motion, and for alpha stable process, I learned from Davar that this is also an old result by McKean. I think that 55, I found two references, and then the result is the same here, but with the 2 replaced by alpha, which is a nice generalization. There is a lot of literature on the subject, and old and new. So here I have mentioned some of the results. For example, for Markov processes, so this is a monography, and there are a lot of papers also, multidimensional Markov processes satisfying some peculiar assumptions or particular assumptions, Levy processes, and also in a more abstract setting, there is Michael Regner also and co-others have contributed here, Sapper processes, anisotropic Gaussian random fields, and so on. Okay? And I would like to point out these 2 references, this one because it's the classic and standard of the, well, with a lot of interesting results on the relationship between probability and analysis, and the book by Hosnevi-san, which is really a very good reference if you would like to know the subject. So as a second example, I would like to talk about the Brownian sheet. So what is the Brownian sheet? It's a generalization of Brownian motion. So it's a Gaussian process indexed by m-dimensional parameters. So this is a positive with a positive component, independent components also. Okay, independent components centered. And the covariance is given by this formula, where the sign here means the infimum. So this is, if m is equal to 1, of course, you get the Brownian motion. So for this particular case of Gaussian process, the result by Kakutanis and Dvoretsky has been generalized by Hosnevi-san and Shi. So the heating probability is upper and lower bounded by the d minus 2m dimensional Bessel risk capacity. So if m is equal to 1, you get the result by Kakutanis. And this is an important generalization because although the Brownian sheet possesses a type of Markov property, the available results on Markov properties couldn't be applied to this situation. So here in the proof, they use new ideas coming also from two-parameter Ito calculus or multi-parameter Ito calculus. So let's go further with the generalization, and now I will talk about the generalization of the Wiener sheet in the case where the parameter is two-dimensional. So now m is equal to 2. Okay. So consider this system of SPDEs. So this is the differential operator. Okay. So b and sigma are the coefficients. So assume that they are nonlinear. And this is the formal derivative of a two-parameter Brownian sheet. We give initial conditions on the axis, so the evolution is in the positive quadrant of the plane. And of course, if v is equal to 0 and sigma is the identity, then you obtain the Wiener sheet for m equal to 2. But of course, it's a qualitative big difference between this example and the Brownian sheet, because here you have a nonlinearity, so it's much more complicated. So Dalang and Eulalia and Mollard, actually this was the thesis of Eulalia, have generalized the result on Brownian sheet for the solution to this system of SPDs, assuming a kind of Hormander type conditions of non-degeneracy on the vector fields defined by sigma. And the result is that one. So as you see, is exactly as sharp as in the Gaussian case, because 4 now stands for 2m, m is equal to 2. Okay? So this was really a remarkable result in the sense that in the Gaussian case, in the previous examples, you could deal with a specific form of the density. And I am not trying to say that the results were easy to obtain. This is not the case. But anyway, the form of the density is there, and you can play and with more or less smart calculations. But here the situation is different because the density is not we are not in a Gaussian situation. So what are the key ingredients for this, or what have been the key ingredients for this extension? So the first ingredient is that using Malevin calculus, it was proved in an old paper by Noillard and myself, so David Noillard, the father, that the solution of such a system of equations under appropriate Hormander conditions possess a density. And then later on, Kohatsu Higa proved that these densities had nice lower bounds, so properties of the density were proven later. On the other hand, in the proof of the result, also some ingredients of two-parameter martingale inequalities were used, mainly Cairoli's maximal inequality. And so this technique was initiated in a seminal work published in Acta Mathematica from Cairoli and Walsh. So these are the more important ingredients. And in fact, the fact that these martingale inequalities are available in this setting is the reason why the upper bound could be expressed in terms of the capacity. So this is not the case in general. So in general, we will aim to obtain upper bounds in terms of the Hausdorff measure and lower bounds in terms of the capacity. Yeah. What is the situation concerning SPDEs? So the case of the heat equations essentially in a spatial dimension k equal to 1 is pretty well understood. There are well, very complete results, and here I have quoted what I think are maybe the most important ones. So starting with that one, with no drift, so v equal to 0. Then also the case of a heat equation with reflection has been studied. The case of additive noise, the case of multiplicative noise, and in work in progress, I know that Dalan, Hosnevisan, and Noalar are studying the case where k is greater or equal to 1. So essentially, in these references, the noise is wide in time and in space, while here there is the noise should be correlated in space. But so far, there have not been results concerning waves, at least not very general results. So what the plan with Robert was studying this question of heating probabilities, or upper and lower bounds, for stochastic waves. And we decided to start by looking at the proofs of what was published till the moment, and see what are the essential ideas, and maybe write some general lemmas that could be used also in any possible situation. So then I will report on that. So summarizing and not giving the details will come later. We have seen that lower bounds for heating probabilities can be obtained as far as we have two ingredients. One is a sort of Gaussian type bounds for the joint densities of the process. And as a second ingredient, we need that the density is strictly positive, or well, some property like that. So this is need to obtain the lower bounds. While for upper bounds, what is need is boundedness of the density on compact sets and estimates of LQ moments of increments of the process. So more precisely, here you have the result for the lower bound. So this is an abstract result. Assume that for any two different points x on y, the random vector vx, vy has a density, has a joint density. And assume that this joint density can be upper bounded by a product of two factors. So one factor looks like that, and another factor is looks like that. So it's an exponential. So this looks very much as a Gaussian density. Okay. So normally this gamma, when we'll apply this result, or well, we'll try to check this assumption, gamma will depend on the dimension d, and also on the type of stochasticity that is in the random variables. Okay. So the second hypothesis is that density should be strictly greater than 0 uniformly on compact sets. Okay, so this is what is stated here. So with these two results, an easy application of Paley-Sigmund inequality yields the lower bound of the heating probability in terms of 2 over alpha gamma minus m capacity of the set A. So alpha is the parameter which you see here, gamma is the parameter you see here, and m is the dimension of the parameter set. Yeah?
If you only have condition 2 on some compact, would the conclusion hold for any subset of that compact, or do you really need it on the whole space?
You mean what?
So I took an A contained in K.
This K. Well, this assumption actually has been formulated in different ways. So, for example, one possibility is that you have continuity and non-negativeness also. So, I mean something that allows, yeah, you can.
Epsilon fat.
Yeah, that's fine.
Something that allows you to localize and. Okay, so then concerning the upper bound, so this is the statement. So one need the density to be bounded also on compact sets, and actually also in a small compact set, but anyway. And then we need this condition here, which is, as you know, related to the regularity of the sample paths of the random field. Okay, so this in particular gives you delta Hilder continuity of degree strictly less than delta. So if you have, with these two conditions, one can prove this upper bound in terms of the Hausdorff measure, and here the parameter of the Hausdorff measure is zeta, so zeta can go till the dimension d, but excluded, minus m over delta. Delta is the parameter you have here. And in fact, for a class, a particular class, I will not precise, a particular class of Gaussian processes, one can reach the D. Okay, so for Gaussian processes, this, the result can be improved a little bit. So let's apply these criteria, or this analysis, to systems of stochastic waves. So the equations we will consider, the system of SPDEs we will consider, are of this type. Okay, so this is the stochastic forcing term, this is the free term, and we are interested in systems in principle of any spatial dimension k. So then we'll see that some results don't apply to any dimension. And the noise I have put here is a noise which is Gaussian centered, and it's stationary in space, and the covariance is given by this formula, which is also formal. So this is the Dirac measure, so that means that the noise is white in time, the components are independent, so this is the Kronecker symbol, and they are correlated in space. And here, for the sake of simplicity, I take as a correlation, a risk correlation. Some results hold for more general covariances. But anyway, so let's consider this example. And for the coefficient sigma and b, I will assume continuity, Lipschitz continuity at the moment. So there are these type of equations have been studied by several others, and they are well understood. So starting in dimension 1, then in dimension 2, in dimension 3, this is exactly, well, the type of results we need. There are also results in any dimension k, and other approaches as well. And of course, the list of reference is by no means complete, but anyway, have to stop somewhere. So let's start with the analysis of the Gaussian case. So under the name of Gaussian case, I understand the case where the coefficient sigma is just a matrix with constant entries, non-degenerate, so the determinant is different from 0, but I am not considering any drift, so b is equal to 0. Okay, and well, also for the sake of simplicity, assume that initial conditions are null. So this, in fact, is well, it's not really an equation; it's a definition of the random field U. So that means that the random component, the ith component of the random field U, is given by this expression here, which is the stochastic convolution of the noise with the fundamental solution to the wave equation, whose Fourier transform has this expression here. Okay. So let's consider this process. So now we are in the Gaussian case. So this is the easy situation. However, this example is important because when we'll try to generalize the results to general, so nonlinear waves, this will give us a guide for what is the optimal result. Okay. So this is the result we have proved. So if you consider compact sets, so in time we have to exclude 0. So t is an interval which doesn't contain 0. and G is another compact subset of K. So this result is for any dimension K, for any special dimension K. Then the heating probability to a set A is upper and lower bounded by the Hausdorff measure and the capacity, respectively, of order D minus 2 times K plus 1 over 2 minus beta. So remember that beta was a parameter associated with the description of the smoothness of the noise in space. Right? So then you can, from this result, and since this result is obtained, as I will show you later, applying the criterion. Okay, so that the criteria. So that means that in principle, if you change dimension, you should be able also to give answer to several questions. For example, you can here fix time and consider the section of the process in time, or fix a space and consider the section, and then what you expect is a change in the dimension. So here K plus 1 is the dimension of the parameter space, 1 for time and K for space. Okay? So, for example, for the sections in time, you get this result, okay? And for the section in space, you get this result. So these results actually can be obtained also in using a different approach, and this has been done in an almost simultaneously paper published last year. So that these Birmela, Cohen, Chow are not using the sort of criteria we have produced, but anyway they reach also the same result. But their method doesn't apply to more general processes. Okay, so then with these results, we can, for example, answer the question when is a singleton a polar set for the Gaussian stochastic waves. And the answer is the following. So assume that A is polar. So remember that polar means that the heating probability is 0. Okay. So then since we have upper and lower bound in terms of capacity in Hausdorff measure, that means that the capacity should be 0. Okay, and this can only happen if this parameter, which was this parameter, which was the parameter which appears here, is positive, because otherwise the capacity will be 1. Okay? So this is a necessary condition. Then the other way around, assume that this number here is strictly positive. Then the Hausdorff measure of a singleton, since this is positive, is 0, and therefore A is polar. So of course, would like to have an if and only if. There is one case which is let, so we don't know what happens if this is equal to 0. Would like to have this result, but this in principle should not be easy, because in the case of heat equation, for sigma constant and B different from 0, actually this is part of the results of Miller and Tribe, so it's an article. So let me sketch some ingredients of the proof of this theorem, because then we'll find the same sort of problems in the nonlinear case. I will not give all the ingredients, but some of them. So one important thing we have encountered are properties of the density, and essentially these properties were boundedness, okay, upper and lower bounds. So here things are pretty easy. In the sense that since we are in the Gaussian case, the density is explicit. Okay, so this is the variance of our stochastic process, and well, it's not very difficult to see that because of the explicit form of the covariance of the noise, the covariance of the process is given by this formula. And then it's also not very difficult to see that this expression is upper and lower bounded by these quantities. And this gives you, at least in this case, this gives you immediately the properties of boundedness, upper and lower bounds that are neat. So another very important ingredient is that one. So here what we have proved is that for these Gaussian stochastic waves, the L2 moment of the increment is upper and lower bounded by up to a constant by the same quantity. So this is important for several reasons. So one reason is that, of course, by hypercontractivity, you obtain immediately a similar upper bound for the LP moments, okay, which was one of the ingredients for the proof of the upper bound. So on the other hand, of course, this gives you also via Kolmogorov's criterion the Hilbert continuity of the sample paths. But since you are in the Gaussian case and you have also the lower bound, this regularity is sharp. So you know exactly what is the regularity of the solutions of Gaussian waves in any dimension k. Okay. Because of this property, we can prove that the improvement we have on the Gaussian case also holds. And this result is also used in founding the upper and bound of Gaussian type for the joint densities. So the upper bound, this is always the hard part of the problem. So here the joint density of the process at two different points have the required upper bounds, and this is proof. So the idea, roughly speaking, is the following. So here, what you do, so this is the notation for the joint density, what you do is, well, the normal trick. So you disintegrate the joint measure into the product of the conditional and the marginal. Okay, so this is the conditional density and this is the marginal. Okay, and then from the conditional, so we are in the Gaussian environment. From the conditional density, you get two type of terms. One is that one, which gives you the measure of dependence or independence. Okay, so this comes from the conditional covariance and an exponential term, and this also gives you two terms. One is just you upper bound by a constant, and the second one you put it together with the exponential part of this, and altogether gives you that. Okay, so here you have exactly the sort of hypothesis you need for the lower bound. Okay, so remember that in the criterion, so in the upper bound, we need that to be certain gamma and that a certain alpha. So here alpha is equal to 2 minus beta. So you see the dependence on the noise, and here the gamma is that. So you see the dependence not only on the noise but on the dimension. Okay. So with these ingredients working a little bit hard, so you can apply the criterion and found that the lower bound in terms of the capacity of this order, which if you replace gamma by its value and alpha with this value, you get the d minus 2 times k plus 1 over 2 minus beta. So this is mainly the most important ingredients that are used in this case. So now let me go to the general case. So what do I mean by general case? So general, so it's like general in the case that in the sense that now k it's restricted to dimension 3, so 1, 2, or 3, and now the coefficients sigma and b are no more constant, and either b is 0, so they are general. They are bounded, infinitely differentiable, bounded with bounded partial derivatives of any order. Okay? So these are the assumptions. And then we need also a non-degeneracy. So the hypothesis is uniform ellipticity, okay, which is explained here. And will restrict to densities given by risk kernels of order beta in this interval. So this is the general situation. So now let me explain the results. So concerning the upper bounds, we have the following result. So we fix compact sets in time and in a space. So here no need to go away from 0. And you have an upper bound of the heating probability in terms of the Hausdorff measure of the set A of this dimension. So the delta is arbitrary, so delta can be arbitrarily small. Okay, so this is almost what we found in the Gaussian case. In the Gaussian case, we found d minus 2 times k plus 1 over 2 minus beta. And here we have a slightly less parameter, so arbitrarily close to d. And we can also prove analogous results for the sections. So just well, you get what you guess. So if you fix x, now the dimension is 1, so you have you get 2. And if you fix time, now instead of k plus 1, you have k. So what are the ingredients to prove this theorem? So they are given in the criteria. So we need existence of density of the law in this general situation. We need a boundedness of the density. This is for the upper bound. And we also need LP estimates of this type for some delta. Okay? So all these results, so they are not easy results, but more or less there are in the literature. Essentially, if you restrict to a system of dimension 1, which here is not interesting at all, but anyway, the proofs can be generalized quite easily. I would say that, well, maybe the most relevant references for that are those ones, and in particular, we'll use a lot results, not only not only the result which states this property, but also techniques which we use in our article with Robert, published in the Memoirs last year. So this is for the upper bound. So now, what about the lower bound? So for the lower bound, you have something which is a little bit different. So I will report on that quite extensively in the last part of my talk. So for the lower bound, we have to restrict to intervals of time which do not include 0, and then the result is that one. So the heating probability of the set A is lower bounded by the capacity, and here you see that there is a change with respect to the dimension of the Hausdorff measure. So here, instead of having, I will compare, maybe it's better. So instead of, I am lost. So instead of having d minus delta minus 2 times k plus 1 over 2 minus delta, so considering this case, we obtain something which is greater than 1, because here I have 3 minus beta over 2 minus beta. So if here instead of 3 minus beta we would have 2 minus beta, then both parameters in the upper and in the lower bound will be the same. Okay? So I will talk about that a little bit later. So and this is the corresponding results for the sections, which are so analog. So now the remarks. So the upper bound is almost optimal in the sense that for the Gaussian case we have obtained that dimension, and for the non-Gaussian case it's just as close as you wish from D. But for the lower bound, we have a discrepancy. So in the Gaussian case, we had this value, but in the non-Gaussian case, we had this value. As you will see, this is due to estimates of the small eigenvalues of the inverse of the Malevin matrix. I will try to report on that in a few slides. So this result, this result is fresh baked. So I think that we have finished it last week. Okay. So it's very difficult to prove this result, and well, we have devoted a lot of energy to it. We have checked all the details in the case where V is different from 0 and sigma is constant, so we are absolutely sure about the correctness of the result. And now we would like to have a rest and to look in a week from now at all the computations we have done in the nonlinear case. But we are pretty sure that everything is okay. But anyway, it's so involved that now we need a rest. So what are the ingredients of the proof? So from one side, we need the strict positivity of the density. This again, as I told you before, there are extensions of results that are written in the literature, but still they have to be updated. And here I give references for that. And you also need, well, several ingredients, but I am now giving the most important ones. So Gaussian type bounds for the density. So remember that in the case of Gaussian waves, the upper bound we need was of that type, okay? And they were obtained in the Gaussian case using very much the structure of the Gaussian density. So here, instead of using the structure of the Gaussian density that we have anymore, we will use Watanabe's formula for the density, which is an easy consequence of the basic integration by parts formula of Malevin calculus. So what is this formula? So this formula looks like that. So the joint density of our process, the solution to the nonlinear stochastic wave, is given by product, so this is because of we are in dimension D, of the expectation of the product of two things. So one of the terms here is very easy to understand. The other one, I will not give the definition, but this is a random variable which depends on the two random variables which we are considering, and it's built using Malevin derivatives of u at the different points, and also the inverse of the Malevin covariance matrix. So in the Gaussian case, the covariance Malevin matrix is just the covariance matrix, okay? But here, well, this is random, and this is much more difficult. There are also other ingredients that are in the definition of H, but I won't give the details. So then the situation is as follows. So you have also a product of two things with expectation, and then, well, by Hölder's inequality, so you split this expectation into two parts. And then you have to deal with this probability and with the L2 norm of this random variable. So let's report on the contribution of the L2 norm of this random variable. So the result says as follows: assuming the assumptions I have shown you before, this L2 norm is upper bounded by this quantity here. And it is here where the parameter gamma, that we didn't want to have that way, but instead with 2 minus beta, appear. So this is this is connected with oh my god. Okay, so again I stress this fact. So this is connected with the estimates of the small eigenvalues of the Malevin matrix. Okay, so in general, when you deal with Malevin calculus, the LP moments of the inverse of the Malevin matrix all what you want is that it is bounded. Okay, so we like to have that the inverse has moments of any order, something like that. And then you only need to prove that the smallest eigenvalue has an inverse which is integrable of any order. Okay, but here we need the rate of degeneracy of these small eigenvalues. Okay, so this is why the upper bound we need is not just a constant, but a factor which takes into account what happens when the 2 points are close to each other. And this is the main difficulty. So these estimates of the small eigenvalues and also of the large eigenvalues, which well, the result is different, but anyway, so this is what we need. Okay. And at the end of the talk, I will try to say why here these 3 minus beta appear. So this is one of the ingredients, and then the second one is the contribution of the tails of the distribution. So these probabilities. Okay. So in the case where b is equal to 0, so more or less we are in a martingale situation, in the sense that we can associate with the solution to our system a martingale. And then if you have that, you can use exponential martingale inequalities, and you have an upper bound in terms of an exponential. Okay? But we are interested in the case where b is not equal to 0, and we are in dimension which can be greater than 1. So in particular, we are interested in dimension 3, which is the difficult one. So then there is no suitable Girsanov type theorem that allows to go from the equation with a drift with the equation without a drift. So here the strategy has been different. And actually is a quite easy idea, but well, one has to have this idea, is the following. So in order to get an estimate of this probability, what we'll do is keep track of the property we have. We have sharp properties on the estimates of LP moments of increments. Okay? So we just apply Chebyshev here. Okay, and use the properties that we have proved in order to establish the Hölder continuity of the sample paths. And we end up with an estimate of this type. So of course this is much worse, as that here is exponential, here is a potential, but it turns out that our criteria for getting the lower bound estimate of the joint density can be modified, and in fact what we need to get the Bessel-Ries kernel is just to have an estimate of the tail probability like that. So this is sufficient to study the case where beta is different from 0. Okay, so these are the ingredients, so very, very flashy, because as I said to you, is really a very involved subject. And here are the main references that we have been using. Okay. So essentially, the method of the proof. So the method is the method that has been set up here. But as you know, waves and heat behave very differently. So as a guide, it's okay. So we have followed what we have done, but then the problems we encountered were completely different. Okay. So and finally, thanks, and especially I would like to thank the organizers of the program. It has been really a great time to be here, and especially because you provide us with the conditions to carry such a work, which is really devotes thanks, great thanks.
Yeah, thank you very much. Any questions or comments?
Yeah.
So your Gaussian noise, is it a strong multi-parameter martingale in the sense of Karelian-Walsh?
Here we are not using that. No. Here what we do is, well, you freeze one parameter, okay, so you have stochastic convolution. So you can freeze a parameter, okay, and associate a martingale, a multi-parameter martingale, which is given by the indefinite integral. Okay, and then we apply the exponential inequalities to this martingale.
And is it just dictated like by sharpness of bounds ideas? Why did you choose this particular covariance?
Sorry?
Why did you choose this particular covariance for the Gaussian noise? Is it sharper bounds?
No, this is because, well, for several reasons. There are historical reasons, and also because, for example, the Hilderianity, the Hilderianity of the solution of stochastic waves have improved under this assumption. Also, the existence of the density. So what happens is that, well, with this sort of covariance, we can apply tools of harmonic analysis. For example, if you look at our paper in the memoir, we will see that Hilderianity we got, which is sharp, is the same as in the Gaussian case, was using very much the semi-group property of his kernels. So it's quite structural, actually. Yeah, thank you.
I just wanted to follow up on Anna's question, which is, so of course, these vessel kernels, these kernels are very natural, as you mentioned, for a number of reasons. They interpolate also between white noise and
Exactly.
But what if the covariance is smooth and nice? Those equations are also important equations. And with these methods, any chance at,
Well, some of the they should be, for example, in the to prove the Hilbert continuity of the solution of the stochastic wave equation. So I am sure that it works with other covariances. But you are not. I mean, I don't know how to prove sharpness. Okay, so the sharpness of the result. So you will get a Hilbert continuity, which is not the one you get for Gaussian. So because of technical reasons. So the big problem, maybe in dimension 2, I think that you can improve the results that are available. But in dimension 3, it's if you consider general covariances, it's a real mess because you know the problem is that since the fundamental solution is a measure, so you encounter the problem of dealing with the difference of two integrals, and you cannot apply Burkholder's inequality there because you need positivity, and so I am not, well, it's difficult to say because, you know, it can be that people have great ideas and go through this hard problem, I don't know. But this is at least one of the reasons why. And another thing that I don't know if you are interested in is why there is the 3 minus beta instead of the 2 minus beta. So does the president allow me 1 minute more? Yeah? Okay. So it's difficult to, 1 minute, yes. It's difficult to explain, but I will try to be very, very sketchy. So the situation is as follows. So you have to deal with the inverse of the malleable matrix. And something that you have to, you see, if I write here, something that you have to study are lower bounds for integrals from 0 to t and with respect to time. And here you have some norm, which is actually associated with the covariance of the noise, so the auto-reproducing kernel Hilbert space of, and here you have the fundamental solution of the equation. So let's put something like that, and then here some stochastic process, okay? Some stochastic process sigma. And you have to lower bound that. So then you can lower bound that in 2 ways. So and you would like to localize around the singularity. So you can do that in 2 ways, either in space or in time. So if you are dealing with a space-time while noise, this is an L2 norm. So you can either localize in time and in a space, and then you get the 2 minus beta. But here, we have localized in time. So it's much more complicated than that, but keep this idea. Okay? Localizing that way, which means, for example, in dimension 1, so in dimension 1, you have the light cone. Okay, so this is Tx, and when you localize in time, actually what you do is integrating in this part. Okay? And this is very small. Okay, so this is very small, and this is what gives us the epsilon to the power 3 minus beta. So an alternative way to proceed is to localize in a space. And if you localize in a space, then you will integrate on these strips. And since these strips are bigger, then you have more chances to obtain the epsilon to the power 2 minus beta. But what means localizing in a space? So what happens is that this norm is an involved norm. So this norm, how to say, so this is something which is not positive. Well, the norm is positive, but this is something like that. So here you have G, T minus S, U, T, T minus S, V, and then sigma at U and sigma at V. Okay? And if sigma is not positive, you cannot lower bound that by localizing in a space. So a similar problem happens when you are studying, for example, the existence or regularity of density for equations, for stochastic differential equation, not SPD, driven by fractional Brownian motion. This appears in your article in, with Baudouin. Okay, so it's the problem is that so here, except if sigma is positive, you cannot give a lower bound by localizing. So one possibility is what we have you have done. So try to find a lower bound of this norm in terms of another norm, or try to stick on examples where this is positive. So this needs another program.
I come back to that in a minute. Any other questions? Okay, I have a question. I mean, maybe I missed that point. In your general result in the nonlinear case, you said the constant, the appearing, they depend on whatever dimension and so on. But they should also depend on probably the Lipschitz constant of the nonlinearity.
Yeah.
So the Lipschitz constant comes in, or just
the Lipschitz constant too.
Comes in.
Yeah, because for example the Lipschitz constant appears, of course, in the LP norms estimates of the increments. So yes.
Because
so the structure.
So I wasn't.
No. Of course, of the structure of the problem. Yeah. So when
Just one quick question. So I mean, I was just wondering, there's this other set of techniques for showing positivity, right? That go back to at least Benarus and Leandro, right? Where you have some connecting path in Wiener space that carries positive density with it, right? Because the Maillard covariance matrix is non-degenerate in a controllable way along that path, right? I mean, it seems. I was just wondering if those ideas have been used in this setting.
No, it's different. No, it's more the so a control of the non-degeneracy of the density. Well, we are not using that, but it's a similar problem. I agree with you. Yeah. We are not using. We are not using techniques of that article, but I understand what you mean, because there is a non-degeneracy when USX is equal to USI, and somehow we have to control that.
Versions, there's a real difference in the sense that you need some kind of a much different. I mean, kind of along a particular path. You need to know that it's non-degenerate, right? You just having the kind of probabilistic estimates. Like, I mean, without the kind of local Holder regularity type estimates you have, but just using the probabilistic estimates on the smallest Maillard the smallest eigenvalue of the magnetic covariance matrix only gives you, you know, C infinityness of the density. It doesn't actually give you strict positivity.
Maybe we should continue
should
this
talk about this
during
later, sorry,
the
yeah,
coffee break.
yeah.
Because probably people are now really longing for coffee. So just one week, I mean, I have to make an announcement. I mean, thank you very much stuff, but there's one more remark I should make here, because your kernels, I mean, they have to do with non-local operators. And if you look at those kernels, they're related to the same things that Caffarelli was talking about here, because they're proving now very hard estimates on this stuff. I mean, they prove Harnack inequalities for these operators. There's also Kasman and Bielefeld working on that. And I think this is one features of this program, to bring together deterministic sort of cutting-edge research on PDE and also on deterministic PDE, and on the other side on stochastic PDE. And I think this is really a very beautiful point where these things come together. So I think Jonathan's idea are exactly right, because what behind is just the same thing for jump processes, what Kusoka and this Belarus and later on Belarus and so I think this is a very nice contact. The other thing, I should give you thanks back to you, because you organized one of our many special semesters at Mittag-Lehrklasse. So you are definitely knowing exactly what we're talking about. And I think we should think about further semesters in the future, Robert. So I think it's very important, I mean, to do this every few years. And there's another possibility, if you have something which is really between applied and theoretical. So that means you, for instance, you want to work with people in meteorology or people from physics, so it should be interdisciplinary. Then in Bielefeld we have the Center of Interdisciplinary Research, and you can apply for a semester, even a whole year. You can get up to €500,000. So if you have a good program between areas, that's very important. Then you should definitely apply. Go to the homepage of Bielefeld CIF, and then, so if you want to work with people in biology, whatever, life science, this would be really perfect. And I'm just by chance one of the directors. Okay, so now let us thank Marta Sanz again.